Sorry, Harm, for putting your picture in there. Okay, so yeah, I'd like to give a fairly quick report on some work that both Harm and I did with our student at the time, Alvaro, just looking a little bit more deeply into the level of systematics in hadronic models in a kind of lower energy range than people are typically considering. Okay, so I don't think I have to spend any time convincing you why hadronic interaction models are important. We already had a really nice review talk in this conference. But just to say that a lot of work has obviously been done on these, incorporating data from the LHC. But well, one thing that you might have noticed from the review talk the other day was when people typically show comparisons to data of the models, these end at about 10 to the 15 EV. But it's worthwhile remembering that there are other instruments out there operating in lower energy ranges, so the kind of TeV range, and most notably probably these are gamma ray instruments. Now, in the past, typically, of course, gamma ray instruments haven't been so bothered about understanding the hadronic background very well, because we've been able to play this game of, okay, we take a field of view and we say, well, we think our source is here. Let's look somewhere else within our field of view, and we can assess the level of background in there. So we don't need to worry so much about exactly how our background behaves, or being able to simulate our background very accurately. But if you were there for Lars Moorman's talk the other day on Westerland 1, he then showed this kind of this field of view over here of the Westerland 1 region. And once your field of view starts to look a little bit like this, it gets more and more difficult to estimate the level of background in your data. Now, there are ways of doing this using your data, but certainly we would be a little bit more confident about it if we felt like we could simulate it accurately. But the situation sometimes gets even worse. So in the case of measurements like the cosmic ray electron spectrum, there is no source-free region. So you really have to directly use simulation. So this plot on the right-hand side is essentially comparing simulations to data to estimate the background contamination. And ultimately, you end up with a spectrum where the most significant source of uncertainty comes from the hadronic interaction models. So the work that Harm and I did were prompted by this study by Michiko Ohishi. And essentially what she did was she took the hadronic interaction models that were most up to date at the time, ran them through the entire simulation chain that's used for the CTA observatory, and look at the output at the end to see basically how much does this affect your sensitivity. And what you see at the end is, well, okay, something like a 20% difference in sensitivity from model to model, and even something like a 50% difference in your background rate at high energies. Now, okay, that might not sound like a big deal because, okay, it's just a sensitivity curve, but I don't know, this 20% over here is probably 10 or 20 million euros worth of telescopes. So we do need to be concerned about this a little bit. But of course, like I said, this is all run through an entire simulation chain. There are telescope simulations, data analysis going on. So what Harm and I wanted to do was kind of take a step back and look at slightly more basic parameters that are a little bit easier to interpret, to understand a little bit more what's going on in the air showers. So of course, probably the easiest things to look at are just the lateral distributions in the spectrum. So this is where we started, and we simulated a large number of vertical showers for, well, okay, the most up-to-date set of models at the time, simulating at 100 GeV, 1 TeV, 10 TeV, 100 TeV, and looked at the ground level data at 4,100 meters, which is about the height of Hawk. And well, concentrated on looking at the signal from electrons and from muons. So okay, you see the LDF and the spectrum for APOS here, but of course it's completely impossible to read much from this if I start layering 4 models on top of one another. So essentially what I'm going to do from now on is make these plots and divide everything through by the APOS model. No particular reason for APOS other than it kind of sits in between the other models, so it's more convenient for the plots. And what we have in our plots here is on the left-hand side, the lateral distribution of energy deposit for our electromagnetic particles, a number of particles for our muons. So this is roughly behaving like how a water Cherenkov detector would behave, and compared for 10 TeV protons and 100 TeV protons. And okay, as you can see, there's not really much going on in this plot. Basically, all the models seem to match up with one another rather nicely within about 5%. And just to give you an idea, because often you lose this information in plots like this, of basically where all the particles are, so where the largest number of particles are. The vertical line here marks the median in particle number, and the 68% containment radius is or the 68% containment area of particles is the gray band. So this is really telling you where all of your particles are. So okay, everything looks okay at 10 TeV and 100 TeV, but when we start to get lower in energy, we see the differences get rather large. So if we concentrate really on this 100 TeV shower, basically we're seeing the kind of inverse behavior that we're used to. The lower in energy you get, the bigger the systematic uncertainties on the models become. And you end up seeing, well, okay, I clipped the top off here, but it gets all the way up to 80% difference in muon number between our different models, with QGS significantly overproducing compared to APOS, and URQMD, because we're in the low energy range here, so we can still use this model, significantly underproducing. A similar story seen in electromagnetic particles, in electromagnetic deposit. And well, similar things look rather similar when we go up to 1 TeV, but just to a slightly lower level. So if we investigate these particles a little bit further, so we can just take this central 100-meter region where we're seeing the big differences between models and plot the spectrum of our muons. Essentially what you can see is that the overproduction in QGS-Jet and Sybil that we see is due to high energy muons. The difference is much less apparent when we go to 1 TeV, so that there's perhaps a slightly different explanation there. But yeah, we're very much peaked at high energies here, and the deficit we see on URQMD is coming from lower energy muons. So what's going on here? Why the huge difference? Well, it probably comes down to how the air shower is actually structured. So at 100 TeV, an air shower looks pretty much how you think of it. There are many generations of particle production, and the muons that we see originate from the decay of pions close to X max. Whereas if we drop our energy down to 100 GeV, the number of layers of pion production, number of generations of pion production become much fewer, and most of the muons that we see at ground level are actually coming from either the first or second interaction within our shower. And by the time we've got to ground level of such a low energy shower, most of the electromagnetic cascade that's happening over here has actually died out, and the electrons that we're seeing are instead coming from decaying muons that are actually decaying relatively close to ground level, which then ultimately leads to an equivalent increase in energy deposit. So very clearly, if we think about it in this way, the first interaction's pretty important here. So we can take a closer look then at the first interaction in these energy ranges. And you kind of see what you would expect. So there's a clear peak or a clear excess in high energy muons being produced in the first interaction at 100 GeV of QGS-Jet and Sybil. And like I said earlier, the muons that are produced in our first interaction that are below a few GeV will never make it to ground. They will always decay. So even though they're underproducing now in comparison to APOS at low energies, these guys we never see. They're wiped away. They decay before ground level. So this excess, this peak that we're seeing in this comparison is all that we see when we get to ground level. Again, at 1 TeV, the pion spectrum seems much more comparable. But another area we can take a look at here is to instead look at the transverse momentum. And again, we see that the transverse momentum is very, the transverse momentum imparted to pions in the first interaction is very different between our models. Once we get above about 10% of our primary interaction energy, so again, QGS-Jet's imparting much less transverse momentum, URQMD much more. APOS and SIBOL are kind of sitting in the middle together. And in this case, this seems to scale rather nicely with the primary particle energy. So you can imagine that this plot this plot here is kind of just a stretched out or shifted to the right version of this plot on the left-hand side. So all of this seems to sit together in that the difference in the first interaction seems to well match the differences we see in our shower behavior. Any muons from our first interaction with an energy below about 3 GeV will decay. We don't see them. And then QGS-jet and SIBOL both produce an excess of energetic muons, which are able to reach the ground. And URQMD conversely produces a deficit. The QGS-jet muons, or the additional QGS-jet muons that are produced stay close to the shower core because the pions that are producing them have less transverse momentum. And then these muons get close to ground level, decay, and also give us an increase in our electromagnetic signal. So I think all this seems to tie together nicely. So then the following piece of work we tried to do was to look into or investigate the first interaction a little bit more deeply, this time running a set of simulations where we'd configured our simulation set such that we could simulate our air showers and pick out specific first interaction properties and really compare for a given set of first interaction properties what the ground level behavior looks like. So how this worked in practice is basically you run a Corsica simulation with a fixed first interaction point, you put one observation level directly below that, and then you put one observation level at your ground level. And that allows you to pick out basically the first interactions that are of interest and compare the ground level behavior between them. So we studied a lot of different variables on this actually. Okay, thanks, Alan. So probably the most important of these that I'll talk about is the inelasticity. And if you look at the inelasticity distribution, apologies, I forgot to write that this is 100 GeV. So if you look at the distribution of inelasticities between the models of, well, nucleon-led shower interactions and pion-led, well, first, you can see some pretty significant differences between the different models. So probably the biggest and most alarming one, and it's actually quite difficult to see here, but if we follow the URQMD curve all the way up here, it actually increases all the way beyond our screen here. So URQMD produces a huge number of particles with a very low inelasticity. Now, this is maybe not so bad because then if you look at our table with the cross sections on there, you see actually the cross section for URQMD is much higher than the other models. So clearly there's a balancing act going on here in the way how they've exactly defined their inelastic, what corresponds to being truly an inelastic collision, but fine. Otherwise, around the peak, you see some differences between the models. QGS-jet and APOS are relatively minor. URQMD seems to be a little bit peakier than the other models. So we then split this distribution up into 3 bands, K1, K2, and K3. And essentially what you see is if you compare the low inelasticity band with the high inelasticity band, the driving force behind this, or the driving force behind the difference in the LDF at ground level is really how far your shower is penetrating through the atmosphere. And you see that with URQMD, so in this case, it was a fixed first interaction point. So our tail of very low inelasticities is very important for us here. But in this case, URQMD produces many more particles at ground level simply because the shower effectively starts later. You produce a lot of showers that deeply penetrate within the atmosphere. And this seems to be the driving force actually for the inelasticity in affecting the ground level behavior of the shower. But ultimately, if you plot the number of muons, or the average number of muons as a function of inelasticity, you basically see that these lines are parallel. So ultimately, there's not really any inelasticity-driven changes in shower development here. Instead, what we're kind of seeing is the number of muons that are produced by every model is kind of offset in all inelasticity bands. So I'm on my last slide now, Alan. So just to summarize, I don't think there's too much of a summary to be made here, other than, you know, it's not a reasonable assumption to assume that just because we're at relatively low energies here and we're well within, you know, the equivalent fixed target energy of the LHC, that the models that are tuned to that data will all be consistent. Clearly they're not. And actually, probably these differences mainly stem from a lack of tuning data from the models. First of all, in the kind of kinematic range that's important, coming from the LHC, but also from the detectors themselves. I mean, certainly from this generation of IACTs, we've not really provided any data that models are able to use to tune their predictions from. So just the final statement to make is that hopefully the PO runs at the LHC, specifically including analysis from LHCF and other forward detectors, might help us a little bit to understand what's going on between the models here. But also I feel like if we're going to sort of secure things for the next generation of gamma ray detectors on ground level, we may need to think about making a concerted effort from the current generation of gamma ray instruments to provide something for the model tuners or the model developers to compare these things to in future.